Next presentation is another contributed spotlight from Jacob Andreas.
Good afternoon, everyone. Today I'm going to be talking about learning hierarchical policy representations guided only by a weak kind of supervision that we call policy sketches. So the general setup that we have here today is like we have up on the screen right now. We're in a kind of multitask learning problem, so on some days my agent wakes up maybe in some little kind of Minecraft-like world, and it gets a signal from the environment that says its goal is to make planks. And in this case, the way it makes planks is it does that by going to the tree, chopping the tree down, and then going to some workbench in the world and using the workbench to turn the wood it collected into planks. And maybe some other day, the agent wakes up, and this day it gets a signal from the environment saying that its goal is to make sticks. Sticks are also made out of wood, and so in this case, the agent is only going to get a reward if it goes and chops down the tree to get wood, but then goes and uses some kind of different tool somewhere else in the environment in order to turn the wood into sticks. And so far, this is just a kind of normal multitask learning problem. What we're going to be doing differently today is that we're going to assume that the agent gets just a little bit more help in the form of task-specific hints that we call sketches. And sketches look like what we have up on the top of the screen here. They're essentially symbolic annotations of high-level behaviors. And so our goal is going to be to use these sketches to efficiently induce hierarchical representations of policies with two goals. Both to train faster on some initial set of tasks that have been annotated in this way, and also to be able to generalize efficiently to held out tasks, whether or not we actually have access to these sketches at test time. Before going into the details of how we do this, I want to kind of step back and talk briefly about where this work fits into the wider world of hierarchical reinforcement learning. These sketches that we've drawn up here, right, essentially express the desired behavior that we want from the agent in terms of a small number of high-level actions that we expect are going to be reusable in a bunch of different contexts. And there's a huge amount of work in the literature on learning these kinds of high-level actions, which are sometimes called options or skills, right? And the basic intuition with essentially all of these approaches is that we start by selecting some kind of high-level action. Having selected that action, we use it to generate a sequence of low-level actions, and then eventually this sort of high-level behavior that we're executing either terminates or gets preempted, at which point control is passed off to some other kind of high-level thing. And so the general learning problem we have with these sorts of hierarchical behaviors is to figure out both how the individual operations, the individual high-level actions should behave, and those are the edges pointing down, and then also how to move between these high-level actions, and these are the edges pointing to the right. And it is possible to learn both of these things from kind of unconstrained raw interaction. There's a lot of nice work on the sort of totally unconstrained task, much of it at this conference, but it's a really hard problem. And so a natural question to ask instead is what other kinds of structure, what other kinds of supervision can we apply here to make this learning problem a lot easier? And so one thing that you can do is you can manually specify intermediate rewards that sort of tell you when you've completed one of these subtasks. You can provide other kinds of intrinsic motivation, like for exploring new states. Another thing you can do is actually kind of fill in parts of the whole transition matrix that you wind up with here at both the high and the low levels. And this essentially corresponds to some version of the hierarchical abstract machines framework described by Parr and Russell initially. And another thing that you can do is actually get a bunch of demonstrations of successful traces or even successful policies for individual tasks in your environment and try to extract reusable subcomponents and sort of come up with some sort of factored representation and what's going on. And framed in these terms, these sketches that we talked about at the beginning of the talk look very similar to this. But rather than getting extra guidance in terms of good low-level action sequences, what we're getting is good guidance in terms of high-quality, high-level action sequences. But crucially, we're not going to be told anything about how those high-level action sequences are actually, or how those high-level actions are going to be implemented. So again, right, concretely, some days when we start acting in the world, I know that I'm supposed to make planks by getting wood and using the workbench, but initially I have no idea what it means to get wood, what it means to get to use a workbench. What I do know is that whatever this get wood thing is, I'm supposed to do it at the beginning of both the task I was looking at before and the task that I'm looking at now, and I might also even get sort of a different starting configuration for some other kind of task I've seen before. And I really want to stress how little information is actually communicated by these sketches. What we have up on the screen now is all of the extra information that we're going to use for the Minecraft experiment, or the sort of Minecraft-like experiments that we're going to talk about today. And even this is a lot of bits, you know, because we're sort of putting them in human-readable language. Our agent our agent is just going to see indicators on these things. And so it really looks more like this. And this is all of the extra information that we're getting. This is really very few bits. And one of the nice things is it requires very little effort to actually collect an annotation of this kind, right? You don't have to touch the simulator. You don't have to collect demonstrations from people playing in this world. And you can generate, in fact, this kind of annotation in probably considerably less time than it takes you to do even sort of a single step of your hyperparameter search when you're trying to train one of these things. What we're going to see is that in spite of this, just this little bit of information that we get from these kinds of sketches is going to go quite a long way in terms of allowing us to learn effectively on these sorts of problems. So let's talk about the details of how this is actually going to work. How are we going to use sketches like we have drawn on the bottom of the screen here to learn faster and to learn sort of reusable pieces of policies? And structurally, we're going to do something really very simple. For every one of these high-level action symbols that appears in one of these sketches that we get at training time, we're going to associate that high-level action symbol with some kind of modular sub-policy. And when one of these modular sub-policies is invoked, we're going to call up some sort of neural network that belongs just to that high-level action symbol. It will act for a little while in the environment. And eventually it'll generate some kind of stop action that says it's done, and it'll hand control off to whoever is coming next under the high-level policy. And so for all of the sketches that we have at training time, we're just going to use the form of this sequence of high-level actions that we get to form some kind of concatenated full policy by running all of these individual sub-policies in sequence. And again, when we get some kind of new task with a new sketch that shares some of these high-level action symbols, we'll just reuse these same sub-policies in whatever new context they occur in. And so like we said before, this is super simple. And the real question here then is sort of what function do these little sub-policy modules actually compute? And then how are we actually going to train them? And the key insight here is that across all of the different tasks that we're trying to solve simultaneously, we definitely want to ensure that the behaviors implemented by these sub-policies are the same, but the values of performing those sub-policies in the different contexts where they occur might be quite different, right? In other words, sometimes we want to do the same thing in multiple places, but for different reasons. And this suggests that what we want to be doing here is doing optimization directly over the form of the policies themselves, rather than doing some kind of critic-only method where you're essentially trying to learn some kind of shared value function that may or may not be coherent across all of the different contexts in which we want to invoke it. So just very briefly, and the details are all in the paper, here's the kind of standard form of the gradient that we get from a policy gradient method, but we notice a couple of things that come up in this approach here. The first thing that we notice is that the actual density that gets used in this inner sum is going to vary across time steps depending on the sub-policy that's active at a given time step. So this pi here is going to change depending on which high-level action we're trying to execute at time t. And somewhat more exotically, if we want to choose a baseline that's going to minimize the variance here, that baseline is not going to vary with time for individual tasks, but it is going to vary with the task identity. And so what we wind up with at the end is this kind of decoupled actor-critic objective, where actors get indexed by sub-policies, but critics get indexed by tasks. And we see some potentially dense subset of all of the different ways of combining these things when we train our model. Other than this kind of decoupled thing, it's essentially a standard actor-critic method that we're going to use to train this approach. So just to wrap up here, let's talk about some experiments using this method. Like I said before, we have this kind of Minecraft-inspired task that we've been looking at this whole talk. It is worth pointing out that for the actual experiments we're using here, the worlds are much larger than the cartoons that I've drawn on the screen. The tasks are much more complicated, so things look a little bit more like this. And then we're also going to look at a little maze navigation task where we have to escape from a sequence of locked rooms to reach a goal whose position is specified by one of these sketches. And again, just very quickly here, what we see in the experiments is that this kind of modular agent architecture that we've looked at that uses these sketches to put together sequences of individually parameterized submodules allows you to do a lot better than just conditioning on these sketches as though they were part of the observation that you get of the rest of the environment, and it also does substantially better than sort of existing baselines from the natural language processing literature that work on similar tasks. Doing this decoupled actor-critic thing lets us learn a little bit faster than doing a standard actor-critic thing. And finally, we said at the beginning of the talk that we're also interested in using this kind of supervision to do well on new tasks once we're done training. So the sort of high points of these curves from the previous slides are shown on the left in the sort of standard multitask setting. We can also consider two different kinds of transfer problem. One where we get a sketch for a new task, but we have to do well on that task immediately without getting any time to adapt to that, and that's what we call the zero-shot setting here. And then one that we call a kind of adaptation setting, where we don't get any sketch for the held-out task at all. So we don't have the same kind of guidance we had at training time. What we do get to do is spend a little while learning a policy adapted to this task. And what we can see here basically is that in both of these cases, the baselines don't work well at all. And our approach does something essentially sensible here. So that's pretty much it. Future things that we want to do with this work are look at more complicated kinds of training scenarios where maybe sometimes tasks are missing, where the sketches are provided with real language, or where there's a little bit more structure to the way these goals are assembled. So thank you.
We have time for one or two questions.
Only one with questions. So can you talk a little bit more about how you guys did the conditioned version of this, where you gave those sketches as inputs instead of switching between the policies?
Yeah, so there are a couple of different things you can do. You can literally just provide extra observation features that say kind of the first sketch, here's an indicator on the high-level action, the second step, here's the indicator on the high-level action, and so on. The other thing you can do that, again, looks like the kind of NLP-style instruction following things is to say you get to carry around a pointer to the index of the thing that you're looking at, and then you have some embedding of the high-level action at that index, and that gets fed in just for the particular thing that you're looking at right now as environment features with everything else, and then you have an action that lets you index that, increment that index.
And but what I remember is basically both of those did not perform as well as having completely separate policies.
Right. And I think the question of how much structure is actually supposed to be shared among these things, we're kind of too far in one extreme direction, and you can imagine sharing maybe some like low-level pieces that compute feature representations of the environment, but leaving the high-level things in common. One thing that turns out to be kind of tricky, if you just have embedded representations of the symbols that you feed in down at the very bottom, it's easier to train these kinds of things in a sort of curriculum setting, but in any case, you're always going to learn, you're going to adapt really quickly to the short tasks before you adapt quickly to the long tasks. And so you can wind up in a scenario where by the time the model has the ability to do well at the long tasks, the sort of predictive distribution at every step is super peaked, and so you don't do enough exploration to find the rewards in the long tasks.
Thanks.
More question?
I don't know how much this may overlap with that, but this idea that you have separate little modules for each, little neural networks for each subtask seems against the spirit, at least, of how I would have approached this. And I just wonder, is that absolutely necessary? Is that, wouldn't we want to think that the modularization would kind of emerge from like learning how to respond to the different instructions and stuff like that? Or?
Okay, so I think there are two different questions here. There's like, is what we're doing here the sort of best possible way of dividing up responsibility for the various pieces of the tasks? And again, for that, I think no, and probably you want to figure out some ways of sharing substructure among these modules so that they don't have to totally relearn the environment representation from scratch. The second question, which I think is more interesting, is like, in general, how useful is it to ever have discrete structures when we're trying to solve these kinds of big reinforcement learning problems or whatever?
Well, I just want to say that I imagine that those things would emerge when useful from a kind of a more distributed kind of framework.
Right, absolutely. No. And look, so here's the thing, right? In principle, you train some kind of RNN backbone for this thing with no explicit representation of what task you're looking at right now. We have seen, I guess we don't have just the RNN baseline here, but for related kinds of tasks, that it's often much harder to learn those things than having just a little bit of discrete structure.
No, no, I want the hints, right? I think the culture, the parent, the sibling, whatever, you know, the world provides these hints. I mean, if you've ever listened to the Minecraft dialogues that my grandson plays with, let's do this now, and let's do this now, and all this. All that language input is there, but the cloning of a separate little neural network to deal with each subtask, that's the part that just seems...
Right, and so, you know, I think, again, what I think you are describing instead looks a little bit like the blue line that we have on the screen for this task, for lots of other tasks that people have looked at. I think we have found that just a little bit of discrete structure in the actual parameterization of the model turns out to be quite useful. We can talk about this more offline.
Thank you.